Just about there. Just waiting out the clock now. Welcome back, everyone, so far. Okay, I think it's official. Welcome back, folks. We're about to finish up our third week, so we're starting to fly through these weeks. It might start to feel like. For the announcements we have today, nothing too major, but we do have our very first quiz due. A lot of people have already submitted it by email. I don't have a specific timeline. I did put, I think, on the system here on Canvas that it's due 6 o'clock. That's just to put a time in. So if you send it to me right now after class, maybe you're finishing up the last touches or getting your scanner working, just send it to me at any time today and it's considered on time. Also, this is going to be our pattern now that we're back on Thursday. I did post this yesterday just so I could get it kind of ahead of my Thursday work week. But quiz 2 is now available, and they're all going to pretty much look like this. You would click on the link for quiz 2. It'll take you to yet another link to download it as a PDF. I like PDFs just because it's as easy, the most compatible way to give them. And then like the quiz 1, you can print this out on paper or just solve it in ordinary lined notebook paper. Take a screenshot of your work, send it to my email address, and you're on your way with quiz 2. So this one looks like it's the topics that we were looking into just last Tuesday, and we'll be looking into again on today as well. So that's going to be our pattern for these quizzes. We'll have one each week. They'll be about the same size as the one you saw here, the one that's down below. And any questions about that so far, folks, about quizzes or otherwise?
I don't have a question, but I have my quiz that was due at 6, just barely done. I'm just having a little trouble finding your email. So that is why I am late on that.
Gotcha. You can find my email in a couple ways. For example, you could go up to, I think it's on the quiz, but I think it could go two ways on the syllabus. And it would be this email right here. Another thing people have been doing is they've been going into, I'm not too sure how this looks as a student. Let me click the student view. You can go into people, just click on my name to send a message to me through Canvas. And people have found a way to upload it that way. I think that's kind of amazing. That would work out just fine as well. But yeah, no worries if you're having trouble getting that first quiz, send it to me. We're pretty much it's like a kind of trial run on the first quiz. As long as you get it to me at some point today, no worries at all. Other questions or comments so far? I'm forgetting where to scroll here. Give me a moment. There we go. That's where it goes. Okay, well, for what's going on this Thursday, we're going to be finishing off section 3.2. Try not to race through it. These are pretty tricky problems. And 3.2 is like the long section in this whole chapter 3. Section 3.3 is going to be the final section that we're going to go through, and that one's actually a little bit shorter. We get a bit of a break after we're done with that. Then we're going to be completely done with chapter 3 at that point. We'll move into chapter 4. What chapter 4 is all about is we're going to just look at two lines at the same time. We'll call it systems of linear equations, and we'll see some of the first word problems or applications that go along with that kind of material. And another thing that I hope is that this class is kind of a little bit more normal. One thing that happened today on this campus, if you're curious, is we had an actual fire drill go off at about 3:25 p.m. No one knew it was a drill because they didn't email us. And we found out later on out in the green over there that it was a drill. So I had actually had a class going for about 20 minutes and I had to cancel it right at that point. It was like this class, some people in class, some people in Zoom. So that was weird to have. First time I've ever done one of those. Weird timing. It's also September 11th, but hopefully no weird issues on this class today. Well, welcome back, folks. We're going to jump then right back into 3.2. Sort of. This is the top of it. This is not where we left off, but I felt like just a quick rundown of what we're doing in section 3.2 is going to be kind of helpful because there really are a lot of ideas in this section and this chapter as well. And we're starting to see our first big set of formulas as well in chapter 3. So far, the major thing we're defining is what we mean by slope. The mantra is that the slope, defined by symbol m, is rise over run. And so one way to visualize that when you see a line like this is, imagine it's a slide, and you start off from here. If you're sliding down, then the slope has to be negative, and that's why we have negative 1/3 on this one. Always reading the graph left to right. And another way we did this was we just looked at the point here at coordinates 0, 2, the y-intercept, point here at 6, 0, the x-intercept. To get from one point to the other, we're going down, but specifically, we went down 2 and right 6. So if slope is rise over run, that's the negative 2 for down 2, positive 6 for right 6, and it just simplified to negative 1/3. So visually, schematically, this is what we mean by slope. How steep the line is can be given a number. Unless it's a vertical line, that one is always undefined. Then, after defining slope intuitively, just by this kind of visual, we put a formula down. Here's how it goes. We've practiced it a couple times. We'll practice it some more in the rest of chapter 3 as we're finishing it off. Slope is the change in the vertical direction, but that just means subtract your y-coordinates. It's the change in the horizontal direction for the denominator, but that just means subtract your x-coordinates. And that's what we were doing over here on this one. We took the y2, which we have 4 labeled, at the y1. So here's y2 minus y1, and just took 4 minus 11. Then we took the x2, which was 3, the x1, which was negative 8, so x2 minus x1 just became 3 minus negative 8, and that simplified to the negative 7/11. So that's what was going on this one for the slope. We calculated a couple more times and then went off to other different kinds of problems. But that's our refresher on what we've done on these notes so far. Any questions about the slope at the moment? Okay. After that, we change gears again. We're using information about a line to come up with its graph. We also would like to come up with its equation as well. So that's what's coming up in some of the next portions of these notes. They told us on part A of example 3, a line has slope 3 and an x-intercept 2. X-intercept 2 is not the big concept. That's what we were reviewing in section 3.1. It's just 2 on the x-axis. But if we have a slope of 3, we took the number 3, wrote m equals just as a reminder, that's the slope. Promote it to a fraction. 3 can be just rewritten as 3/1, so a bona fide field promotion for that number. And we considered the numerator the rise, the denominator the run. But in other words, if we're here at the given point, go up 3, because the numerator is a positive 3 over there, and right 1 for the denominator being a positive 1. That gave us the second point on the line, and at that point, we have a whole graph. So that was the next major new thing about slope. This is right before we ended class on Tuesday. We also talked about if you have undefined slope, your line is vertical. So if you have undefined slope and it passes through 3, 6, you can put the point here or just focus on the x-coordinate and just draw a vertical line. Next thing we'll look at is this one here. Line goes through -1, -3, has slope -7/2. More similar to part A, just for the sake of more practice. So here's our first bona fide problem of the day. Let me hide those notes down there. So we have a given point. We also have a slope. From here, we can immediately say that's m equals -7/2. I'm going to consider the negative as just belonging to the numerator. And that's what I would do for every one of these problems where a negative comes up. And let me just peek to keep the same colors. It's not a good idea to change the colors in the notes. Because I have a negative in the numerator for -7, this is going to tell us that the rise is actually a fall. We're going to go downwards by 7. The denominator, a positive 2, will tell us we go right from 2. So those are just the directions, like on Google Map. It'd be more convoluted on Google Map, of course, but same kind of idea. We'll start at the given point to -1, 3. We're told the line goes through there. And the slope just gives us quick instructions to get to the next point, or I shouldn't say the next point, another point is a better way to say it. So let's draw this out. Let me make sure I have enough space. It's never fun to try to cram it in. We begin with the coordinates xy. Just as a reminder, it's never a bad idea to just throw this on here when you're learning it to remind you the -1 is in the x direction, so it's left 1 on the horizontal x-axis. The -3 is in the y direction, so it goes down 3 in the vertical y-axis. And those are the coordinates for the first point on this line. Now it is slope -7, 2. Oh, darn it. That means my line might have to adjust a little bit on here. Let me see if I can move that around. There we go, just cheating a little bit. Didn't look before I leaped, and it looks like I just need a axis that goes down just a little bit further. Let me try to make that look. Okay, there's a little bit of a blemish here, but sometimes we have to use our imagination. It doesn't have to be a perfect drawing. So now from this point here, the same one we drew, we have to go down 7. So let me count off 7 units. 1, 2, 3, 4, 5, 6, 7. So we're clear over here now. We also have to go right 2, so that's the part in blue. So right 1 would be on the y-axis. Right 2 would be right here. So we went from the given point down 7 units. Right 1 is here. Right 2 would be in this location. Now the 2 points determine a line, so this is the next hard step. Drawing that straight line as best you can. And that satisfies the instructions finally. This is the line that satisfies those 2 given pieces of information here and here. Well, any questions or comments, folks? Getting that first line down? First line for the day, rather. Okay, so now that we have slope, we can see different ways to plot lines. Turns out just a point and a slope is all you need. And there's a little bit more that goes along with this now. It turns out if you wanted more than just the graph of the line, maybe you wanted the original equation. Like in the last section 3.1, we were just starting with the equations. It turns out a really nice way to build out the equation of a line, we'll see another version, is this formula right here, y equals mx plus b. This one's infamous. You probably have dealt with this a lot in algebra and other courses. This is the slope-intercept form of the line. So what's really amazing about the slope-intercept form of the line is you obtain that form as soon as the y variable is solved for. So that's how you get to that position. So already example 4, this one's a problem. It's not in slope-intercept form. And that means there's certain things we don't know about it unless we really do a lot of computation. Once it is in slope-intercept form, it tells us automatically that whatever that number is, the 1 multiplying x itself is not included, but that number in front of x, it could be 5, it could be -7/2, like an example above, that is the slope of the line. And that's amazing. If we solve this equation below for y, whatever emerges in front of x is the slope. And then, but wait, there's more. The b here, whatever that happens to be, is the y-intercept, which means you can plot a coordinate on the graph immediately with 0, b. Y-intercept means the x-coordinate is 0, so that's why you see a 0 there. So this formula line gives you everything you need to plot it, in fact. It reveals the slope, it reveals the y-intercept all at once, and that's a good, powerful set of tools. One way to think about why it gives us the y-intercept is, recall this is saying x goes to 0. If you put 0 in for x right here, well, y is b. And that's why you get this right here automatically for the x-intercept. But any questions, folks, so far with, well, it's called a theorem just to say interesting mathematical fact. But really it's a formula as well, all in one. Any questions about that formula before we practice using it? Okay, let's give it a try. So it says for example 4, there's a couple parts. First thing we want to do is write the equation in slope-intercept form. And this could come in as an exam question, which makes it kind of more of a vocabulary type of question. You have to know when you see this buzzword, slope-intercept form, all this is saying for you to do is solve for the y variable or just solve for y. Also, that's kind of tricky because you have to recognize that's what it's telling you to do. And that's easy to miss if we're on an exam, unless we're prepared for it. So that's why we're here today. You'll see this again in the homework exercises as well. So let me just copy the equation below so it's not just floating in a sentence while we solve it. If we're going to solve for the y variable, that just simply means isolate it on one side. I'll leave it isolated on the left-hand side, matching what we have up here. So subtract 7x from both sides, and negative 1/3 y will equal negative 7x plus 4. Now notice I kept the x in front. If you went 4 minus 7x, that's okay too, no harm done. But what I'm trying to do is match up this format so that we get better and better at using that formula. I want x to come first and then the constant to come next. So I just forced it to be the very first term when I subtracted it from both sides. Next thing we need to do is just eliminate that negative 1/3. But we can do that pretty quickly. Just multiply the left-hand side by negative 3. That means we have to multiply the entire right-hand side by negative 3 as well. First on the left, there's a cancellation. Y is all that remains after negative 3 times negative 1/3. Over here, a little bit more algebra. Distribute here to here. Negative 3 times negative 7 will give us positive 21 times x. Distribute again by the distributive law, and we'll get a negative 12. And that's the first part of the problem. This is now in slope-intercept form once we are right at this stage, solve for y. Let's emphasize this. It's our first time doing it. Now in slope, intercept, form. The second part of the problem says, state the slope and the y-intercept. Well, the slope is just this. We have to say it. You could write out with ordinary words, slope equals 21, but I think a good way to do it is just m. M is always our common shorthand for slope. So I would do it this way. M is 21, and we've done it. We've stated the slope. So that part's done. It also says state the y-intercept. And the way I would usually personally state the y-intercept is just going y-intercept equals 0, comma. I'm matching up the formula from up here, and the thing that goes in is this entire number, including the negative sign. So the y-intercept is negative 12. If you wrote it like this on a quiz, that's completely fine with me. Same on an exam setting as well. I'm writing it out this way because it's the way the formula is stated in the book, but also the homework sometimes wants us to write out this way as well. So just for the sake of practice. And I mean, it is a good reminder. A y-intercept always really looks like this. It's a literal point. So it always has an x-coordinate 0 coming first, and then the number. So if there were more instructions, if it said to plot the line, it's just like this problem right here. We have a point and a slope, and we have everything we needed. This problem is not that long. We already did a lot of stuff to it, but that's kind of nice in a way. If you have to plot a line like this, you could either find the x-intercept and the y-intercept, or you could just get it into slope and intercept form. That does it just as well. But this problem is done. Any questions at all, folks, with slope-intercept form at the moment? Okay, so really important formula here, or theorem if you prefer to call it. That's a fancy way to say just a mathematical fact that's provable as true. There's two ways to use it though. The way we used it in example 4 was we took an equation, put it in slope-intercept form, and then we said what the slope and the y-intercept was. Example 5 is in a complete reverse. It tells us we have a line that has a slope of 5 and it goes through the point 0, -1. And what we want is the equation of that line in slope-intercept form. So it's backwards now. We want this, but all we're really doing now is filling in the information. What is M and what is B? Critically, we have to be careful that they really gave us a y-intercept. So we'll see problems where this is a little different. If that was like 5 and -1, formula up here is not doing us well. It could still be used, but our author usually doesn't use this formula for that. And it does take a lot of additional steps to solve. But if you have a 0 right there, this is an actual y-intercept. And so that means you can, in fact, just write b equals -1. I'm writing out down a b because it reminds me that's what's going to go exactly in that spot here. And then they just straight out told us the slope is 5, so m is 5 from that piece of information. The entire problem is solved now once we go y equals mx plus b, and just substitute in the value of the slope m and the value of the second coordinate from the y-intercept, b. I want to reveal the formula still up there. So our solution is y equals, when 5 comes in here, just go 5. But don't forget the actual variable itself, x. We could lose the whole question in, say, the homework system, Newton, without remembering to bring x in. We could also lose some points on exam because it's important to remember if there is no x here, it's a horizontal line, and this line is not horizontal at all. It slopes by 5. It's kind of steep going up like that. Then you could go plus -1, but it's better to just simplify it by writing -1 itself. So example 5 is faster, right? But it's also trickier because you're taking the formula and just reassembling by substitution. This one's tricky in its own way, but sometimes this version, example 4, feels like the more common thing we do. We take something, put it in slope-intercept form, and then say what are the moving parts. What are the slope? What is the slope and what is the intercept? Well, that's 2 problems using the same formula up here, going one direction and then kind of the opposite problem below. Any questions with this one at all? Okay, let's try out another one then. This time, slightly different instructions. This one is a graphing problem. We want to graph the line by first finding its slope and y-intercept. Well, that's an inconvenient line, right? But recall from the formula above, let's just write it in as a reminder. If you solve for y and put it in the form mx plus b, you get everything you need. You get the slope m and the y-intercept b. And then our ultimate goal of graphing the line is going to be pretty much immediate. So this one is a slightly longer problem. We're doing everything at once. First step is to put this in slope-intercept form. Let's call that step 1. Slope, intercept, form, which is, again, think of that as a buzzword for these lines, solve for y. So in solving for y, we can add 5x to both sides. -2y is then 5x minus 6. Now we have to divide both sides by -2. We'll divide it here. We have to divide the entire right-hand side by -2. Sometimes it's convenient to just express it this way. Every single term is being divided by -2. So now on the left, it's just y. On the right-hand side, we have an improper fraction, but that's okay. It's a good idea to rewrite this as put all the coefficients in front, -5/2, and then multiply it by x. Because we really want to pop out the number m, not have it all mixed together in the fraction like that. Then this part simplifies. -6 divided by -2 is a +3. And we have just about all we need. We wanted the slope and the y-intercept. And lo and behold, this is the cool thing about this form, the slope-intercept form of the line. The slope is just looking at us, but I forgot to call this a step 2. Not much to really say in step 2 other than get the slope and y-intercept. I'll abbreviate intercept again to INT occasionally. So slope is the entire number. Let me put it over here to the left. -5/2. And y-intercept, just because it's called a y-intercept, the x-coordinate is 0. It's a mantra pretty much that we'll repeat quite often. That means whatever number is here goes directly in. We have the slope, we have the y-intercept, and now step 3, graph using this information. So that's kind of fast in a way, right? This could have been a little bit longer problem if we were getting x-intercepts and y-intercepts, because sometimes the numbers are just not nice. You're dealing with improper fractions and all sorts of things, trying to plot them perfectly. But this one says just reveal a slope and a y-intercept, and we have some really nice points to plot right through in a more immediate way. But really, the big punchline to example 6 is it's just more practice using slope-intercept form. Very first thing that we do is plot the y-intercept. It's up here at a height 3, right on the y-intercept. Not intersect, it's all right on the y-axis. Sorry, talking is getting a little hard. Then just a reminder on slope, we think of this as a rise over run. So this is telling us down 5. Denominator is telling us to go right 2. So next point, we're down 1, 2, 3. Here's 4 and 5, and then right 1 and 2 puts us here. So that's our new point. Finally, the original line, or if you prefer writing it down this way in the slope-intercept form, is plotted like this. Let me try again. It's plotted like this. So we got it, folks. That's the equation of the line. Honestly, getting the intercepts wouldn't have been that bad, but again, you might be dealing with fractions whenever something like that occurs. So in a way, this is more convenient. I didn't worry about exactly how to plot that number. This was the easier number for me to plot. So now we have a pretty big toolkit on plotting these kinds of lines. If the instructions requires you to plot in a certain way, it'll always say what the method ought to be.
Just like you were.
Sorry, go ahead. Might have been an open mic, but any other questions so far? Okay, well, there's a little bit more to say in these notes. Again, this section is kind of big out of nowhere. We have a couple pieces of information, some stuff about parallel lines, and some information about perpendicular lines. If you're like me, this is a lot to read. So one thought I had about these notes is, let's maybe copy this and just put in some additional information right here. I'm going to put this down a ways. Sorry if you printed this out, if you're in the habit of doing that. Maybe grab an additional page and put this one in the middle. Let's maybe do just some examples of parallel lines, some examples of perpendicular lines, and then work through what all this information is trying to say to get a feel for how the very next problem ought to go. So it says parallel lines are lines that have the same, are lines in the plane that do not intersect. Sorry, reading was hard there. So just think 2 lines like this, or maybe train tracks, as long as the tracks aren't curving or anything like that. Straight train tracks would be considered parallel lines. We're told parallel lines have the same slope, different y-intercepts. So that rules out lines that are coincident, one line and then another one directly on top of it. 2 different looking equations can give you the graph of the same line in that way, which is interesting. We're also told if M1 and M2 are the slopes of those 2 parallel lines, well, if they have the same slope, M1 equals M2, And parallel vertical lines have different x-intercepts. This one's just kind of a interesting side fact. So let's try to illustrate the first two right here just to get a good visual what's going on before we just dive into using these ideas. What I want to do is draw two lines, and my claim is that they're going to be parallel. Let's use the slope-intercept form just for the sake of ease. I'm going to use color coding for blue to be the first line, green is going to be the second line. And so here's one line, y equals, let's go with the slope of, how about 2, nothing too steep, x plus 1. And, well, that tells me I'm dealing with the slope. M1 is 2. So M1 is the slope of the first line. From here, from slope-intercept form, that would be the slope of this one. And this is just a subscript so that I have a tag to tell between the two different slopes where they came from. Sure, they're equal, but down here, they're not going to be equal. So it's a good idea to have kind of a way to identify them. My second line is going to be y equals, I want it to be parallel, so I have to go 2x. It says it has different y-intercepts. This one has a y-intercept 0, 1. To make it different, we could go maybe -2. That ought to do the job. So this one now has a different y-intercept. On my second line, the slope, the second one, so we'll call it M2, is also 2. And this one has y-intercept 0, 1, where that 1 came from this part right here. One below has y-intercept 0, -2. The -2 came from that part right there. So now we can plot both of these lines pretty quickly and see once again what 1 and 2 is saying. So the plot of this one, we go to 0, 1, so we're here on the y-axis. The slope is 2, but you can think of it as a 2 over 1, which would tell you go up 2, right 1. So here's up 1, 2, here's right 1. That's the second point on this line. Now, very carefully, oh, I kind of missed, but just make your point bigger, and that works. As carefully as you can by hand, draw that line. So that's one line plotted. Then let's just do it again. Similar kind of line, but now its y-intercept is at -2. So down 1, 2 units, intersects the y-axis there. Slope is 2. You don't have to turn it into an improper fraction, but just helpful for the sake of visualization. So where the point was, go up 2. So 1, 2, right 1. And we're right here. So seeing it again over here with the red dot, that's up 1, up 2, right 1. Hang on. That's 1, 2, 3, wasn't it? That wasn't going to look right. Let me try again. So from where we are right here, go up 1, go up 2, right 1. So it ends up right here. And if I drew this perfectly, there's a bit of fudge factor because I am doing it by hand. It's hard to draw like a robot or a computer software. Fudge my line just a little bit to emphasize that's what we're looking at for parallel lines. So these lines are parallel. If we used computer software to plot them, say in Desmos or a graphing calculator, it would look more obviously so parallel. These lines will never intersect in the plane. They just go out forever, never connecting, never crossing whatsoever. They have different y-intercepts. We can see that right away. One's intersecting at 1, one's intersecting at -2. And the key thing is, if we never graph these lines, you would know they're parallel because the slope M1 and the slope M2 are identical. So the key to parallel lines is that part right here, the fact that M1 is in fact identically equal to M2. Not close to equal, dead on equal. So that's our parallel lines graphic. Any questions about those so far? Okay, we want to do this all over again. Now for perpendicular lines, let me try to scroll so we can see as much of this all at once as possible so we can compare. Okay, that's about as scrunched up as I can get it. Well, perpendicular line says they are lines in the plane that form a right angle, meaning the degree measurement between the lines is going to be 90 degrees. Kind of like the degree for like a box, or say that'd be the degree measurement for the corner of a rectangle and so on. These ones are interesting. It says if M1 and M2 are the slopes of two perpendicular lines, then their slopes are negative reciprocals of each other. That's a mouthful. Negative means one is going to be positive, one's going to be negative. And reciprocals of each other means, well, one's going to be the flipped version as a fraction of the other. That's a lot to digest, so that's going to be helpful when we see it as an example below. So you could restate this whole line right here by saying M1 is negative 1 over M2. That's the negative, that's the reciprocal part. Or a whole different way of saying it again is, if they're negative reciprocals, that means if you multiply the slopes, M1 times M2, you would get just the number negative 1. And then another interesting information, it says a vertical line and a horizontal line are always perpendicular to each other. Doesn't matter what vertical line, it doesn't matter what horizontal line, take one and another, and you have a perpendicular set of lines. And our graph will illustrate this part right here. This is the key to getting perpendicularity. And sometimes it does help to think of in these terms. Their slopes are negative reciprocals of each other. So let's try to draw this out once again. Here's where we'll sketch these. Now I want to come up with two lines. And, you know, we have a pretty good line here already. Let's just reuse that one. Y equals 2x plus 1. This has slope m1, just copying from before, positive 2. It has y-intercept, 0, 1. That's a comma. And now I want to put down a new line that's going to be perpendicular, guaranteed. All right, y equals. Now first, let's look at this highlighted part to see what the instructions really are. Negative reciprocals. That means if this is positive, we are going to have to take a negative sign. If it was negative, we would have to take a positive sign down below. Reciprocal means, think of this as a 2 divided by 1. Flip it. This is negative 1 over 2. Now they are negative reciprocals to each other. So this 2 and this negative 1/2 qualify when it says slopes are negative reciprocals. Still need an x in there to make it an equation of a line, or else it's a horizontal line at height negative 1/2. And it didn't say anything about the y-intercept. Y-intercept could be anything whatsoever. Let's go with a plus 1. Why not? Nothing's going to stop us from that. That should work out. Now, slope 2 is negative 1/2. The y-intercept is still at 0, 1. And like before, let's plot both of these lines. Any questions at all going from the 2 to the negative 1/2? That was supposed to guarantee perpendicularity. Okay, so I'll plot the one in blue first. We go up 1. So that's the y-intercept part. Slope is 2, means never hurts to call that a 2 over 1. Go up 1, 2, right 1, and we end at this point. You know, the hardest thing about this to make it really look perpendicular is every one of these spacings has to be close to perfect. So do your best you can. The closer they are, the more believable the picture will be. So I had a point at 0, 1. I forgot to actually put in that point. Point at 1, 2. And here's the line. Now we do it all over again. This one also intersects at 0, negative 1. So I'll just kind of draw it over there as a reminder. But the slope is different. It's negative 1/2. That means go down 1 There's down 1. Let me try and make that as close to the same distance as possible. Right 2. So it would be over here. And now when we go to draw that line, let me try again. It looks like this. Well, that kind of looks not too bad. That looks like this is a square right here. Not perfect, but they do in fact look perpendicular. Doing it by hand is kind of challenging. If yours looks a little bit off, no worries. You need really good graphing paper to get it perfect. But these lines are now perpendicular. These are perpendicular, it's a good one to sound out, lines. The key to what made it perpendicular wasn't the y-intercept at all. That was really just for the sake of convenience. So my line didn't end up all over the place. It was the fact that the slope 2 transferred to the second line as a -1/2, making the negative reciprocal guaranteed the perpendicularity. So that was our quick by hand experiment to get the feel for what both of these big definitions are saying. On the next example is just going to put them to practice. We'll have 3 scenarios. We want to decide if the lines are going to be parallel, perpendicular, or neither, and not by plotting, because again, that's really hard, actually, it turns out. It's easy to plot something, and even with graphing paper, be convinced it's parallel where, no, it's actually not. It's just slightly off. Same with perpendicularity. So these formulas are powerful. It's going to tell us just what the essence of parallelism is and perpendicularity. So let's give this a try right away on example 7. Definitions are back, and let's highlight these 2 big parts. Lines are parallel if the slopes are the same. Lines are perpendicular if we notice the slopes are negative reciprocals. This information here is useful too if you like it. Sometimes people like just multiplying them together to see if they get -1. Well, I'll usually emphasize it this way. So example 7 says, determine whether each pair of lines is parallel, perpendicular, or neither. Really, this comes down to slopes. And we're just so lucky on part A, they're already in slope-intercept form. The y variable is solved on both lines. So on the first one, we have slope m1 equals -2. Highlight that to blue to say that slope goes to that one. On the second line, slope 2, we'll call m2, is also -2. Observe that the y-intercepts are different. That was part of having parallel lines. It's not the same exact line. Because this y-intercepts are different, but the slopes are the same, we'll say these are parallel. Or you might have just wrote down parallel, and that would have done just fine. That one was fast. It was just nice that they gave us slope-intercept form right out. That means the next one's kind of annoying, right? Because it's not in slope-intercept form. We have to compute the slope by getting it into that format. But before we do part B and part C, any questions so far how part A went? Okay, let's give this one a try. We first solve for the variable y, so that suggests subtract 2x from both sides. 3y equals -2x plus 5. Then divide all sides by 3, which means divide every single term by 3. And we have here, let me just get some more additional space. Y is -2/3 x plus 5/3. This part right here is the very first slope. M1 equals -2/3. Then we just do it all over again. Let me see if I can do something about the spacing here. There we go, fix that for us. So now to handle this one, same sort of steps. This time we're subtracting 3x from both sides. So -2y equals -3x plus 10. Now divide all sides by that -2. Over here then, y is equal to, this will be a +3/2. times x minus 5. And here's our second slope. Slope of the second line is now revealed to be 3/2. So the next step is look at them both. There's no way they're parallel because, first of all, one's positive, one's negative. Parallel lines have to have directly equal slopes. But would you say they're perpendicular then, or neither? Anyone see what the case should be for this one? Can be slightly tricky doing this for the first time. If you're not sure, there's definitely different ways you can look at it. Let's try both ways using this, as well as the instructions here, negative reciprocals. Because one is negative and one is positive, the negative part right here in this statement does qualify. Then the 2/3 goes to a 3/2, so it tells us they are reciprocals of each other. And really that's enough to tell us these are perpendicular. Deserves an exclamation mark on that one. But if you want to see it a different way, you can take M1 times M2. I would consider this to be, oh, didn't mean to scroll on this. I would consider this to be more of a check on the problem. Hang on, let me see what happened here. Maybe we can control Z that. That was really weird. Anyways, take M1 times M2. We're using this part right here, and it's really just kind of a check. This would turn into negative 2/3 multiplied by 3/2. But sure enough, when you multiply those, the 2's cancel, the 3's cancel. It's a negative times a positive. So this results into just -1. And that's what this part of the formula, or definition rather, is really trying to say. So we have a parallel line, we have a perpendicular line. Our gut reaction is this one might be a neither, but we have to check this out to really tell. I think we might be able to fit this one on page. Let me put it to right about here. First thing though is notice that there's a freebie on this one. The variable y is solved for on this one, so it automatically tells us that the slope M1 is 1/5. Then we're kind of on our way with that one. We move over to the next equation. This is the one that's going to require some algebra. So first subtract x from both sides. 5y is negative x plus 10. Divide both sides by 5. So all three terms that appear in the equation. Y is now negative 1/5. Oh, and definitely don't forget the variable x plus 2. So the second slope, M2, equals negative 1/5. So now they can't be parallel because one's positive, one's negative. They might be perpendicular, except that 1/5 did not change into a 5. They're not reciprocals of each other. So this is the one that is neither. Neither parallel nor perpendicular on this one. Well, we did, folks. That's the conclusion of section 3.2. Any questions whatsoever with the slope-intercept form of the line or these parallel perpendicular line problems? Okay, well, we're going to go off then to the next section, 3.3. Not quite as long as this one right here. One of the main things about the very next section is we're looking into more ways to build equations of lines. In fact, the section title is suggestive. It says, find the equation of a line. That, I have to admit, that's kind of a weird title. Usually a title isn't a command like this. This is a command statement. But the author could make their own rules. They wrote the book, so we'll go with it. 3.3 says, find the equation of the line. Seems appropriate because example 1 says, find the equation of the line. This one whose graph is given below. And this is going to be a common feature of the equation of the line. write your answer in slope-intercept form. This will be asked a lot on quizzes, exams, and it's asked all over the place in the homework as well. So this is a good habit to get into. But the reminder about that is, the paraphrase is, you're just solving for the y variable. Y equals mx plus b is what we mean by the slope-intercept form. A little arrow there to convey that. Well, if we want to find the equation of this line, you know, it's sometimes a tricky thing to do because they didn't give us a lot of information to go off of. But what is nice is this number right here, a y-intercept, is provided, and it's at coordinates 0, 4, or you might wrote down on paper just that b is 4. That's the b right here that we're referring to. Next thing you can do is calculate the slope. If a graph is given, you could use a formula for the slope, but it's usually just easier to count off points. Let's do it the conceptual way. The slope is the rise over run. So keep in mind, rise can be either positive or negative. You have to go down 4 units and then right 2. The down 4 is the rise for a negative 4. The right 2 is the run for a positive 2. And it just reduces down to negative 2 altogether. From there, we're done. We just fill in the blanks here and here. The equation of this line in slope-intercept form is y equals, first the slope of negative 2. That's what goes into that position. X plus the second coordinate of the y-intercept, that's b, so plus 4. So in fact, it wasn't too bad. We had a nice tool to write the equation down really fast. But what made this problem pretty nice is it was easy to say exactly what the y-intercept coordinate was. The curve was somewhere intersecting here, and I couldn't tell if it was 2 1/3 or 2 2/3. This is also suddenly a much harder problem. And that's what these notes are about. What are the other tools that we can use when we don't know what the y-intercept is? Maybe it's just hard or impossible to read off the graph exactly. But this is the start of the notes. Any questions on getting started with this problem? Okay, here's our brand new tool then. A linear equation in 2 variables can have lots of different forms, but when it's written in this form, we call this the point-slope form of the line, not the slope-intercept form that we're just looking at. Let's actually move this around so we can really get in the middle here and see what's going on with it. Might as well just blow it up as well. It's not working. Let me try again. There we go. Now it's blown up. So here is the point-slope form of the equation of a line. The reasons you want to use this is a nice formula for building an equation. And the major reason we might use it is we don't know the y-intercept. If we did know the y-intercept, we would just recopy the method we saw in example 1. It's called the point-slope form because what it's provided us is, first of all, we have the slope automatically. There it is as m. And it gives us a point on the graph. It's a coordinate to y1 and x1, or better said, x1, y1 coordinate. When you go from this down to this, you have the point here, and it comes back in the formula like this: y minus the second coordinate, x minus the first coordinate. If you also have the slope, you can put everything together in this kind of way. So the rest of these notes is practice using this formula when we need to in different kinds of scenarios to build out equations of lines. It's really our last big formula for the notes in chapter 3 as well. So that's a welcome additional comment, I would say. Any questions about the formula here, this theorem, before we start to use it? Okay, let's practice a few problems. Looks like we're getting short on time, so we won't go too far into these notes. Well, we might make some head segue, but we're not going to try to race through them. The problem on part A says line passes through, well, it's a 0.34, has slope 3. Saying it has slope 3 is kind of nice. They're just directly telling you M is 3, and that's directly what plugs in right up here in the green highlighting. We also have an x coordinate and a y coordinate. We could call this x1, y1 if we prefer. Put that whole thing in blue. That's the point that was provided for us. So if we want to find the equation of this line, we can start by putting down the point slope form. Y minus y1 equals the slope m multiplied by x minus x1. So all I did is copy down the whole entire equation, but this is a really good idea when you're going to practice these kind of problems in homeworks and on quizzes, because it's going to help you memorize this formula so that you're prepared for when you need it on the exam. So now all we're doing now is dropping in information. When it says y1, it's referring to the second coordinate up here. So it's y minus 4 equals the slope m. Make another substitution. We said m is 3. Multiplying x minus x1. This is our third substitution. X1 is a 3, and so it goes there. The things in black here and here are the things that wouldn't change. It's the y1, m, and x1 that we substitute in information. Last thing we have to do is get it in actual slope-intercept form. But the reminder, once again, is that just says solve for the y variable. So a little bit of algebra to get y solved, and we'll have that equation of the line. So let's write y minus 4 equals, simplify the right-hand side by distributing 3 into the group, 3x minus 9. Next, add 4 to both sides, y equals 3x minus 5. That stage, we're done. That's the slope-intercept form of the line. If we had to plot it, we could have plotted it already from this information here. What we really wanted was just a good equation of this line. Turns out, this equation of slope-intercept form is unique. There is exactly one and only one way to describe this equation in slope-intercept form that goes through that point and has that specific slope 3. That's kind of cool in a way. Slope-intercept form is, again, a pretty interesting property. And that's pretty much what the notes look like in this section and the homework problems as well. Just various equation building type problems. We'll try out a couple more, but any questions at the moment? Okay, here's our next one. It says the line passes through 0, 7, has slope -1. From this information, m equals -1 on this problem. But notice this part is special now. It's not like the last point. The last point was just a generic point in the xy plane, but that one's a y-intercept. Sure, you don't need to use, you can, let me say this better, because it's a y-intercept, you don't have to work as hard as you would by using this equation up here. You could just use the slope-intercept form outright. If you did use this equation like we did in part A, there's no harm done. It's a little bit more algebra. You'll get to the same exact answer. But it's important to recognize when you can take a good shortcut like this one. Here, just directly write out y equals mx plus b. B, the second coordinate of the y-intercept, is already provided. It's 7. So that plugs in here. Slope m plugs in there. And it's kind of a fun problem in a way. It's a reminder that some of the problems in the homework are practically a freebie. This one's extremely rapid, whereas the one above did take some good algebra to get through. So here, y equals just negative x plus 7. Then we're done. We can move on with our life, onto the next bigger and more interesting problems on the notes. Any questions or comments, folks, on these two so far? Okay, let's go off to the next adventure of a problem. This one's a little bit nastier. We've said all along that if you want to determine a line on the plane, all you need is 2 points. And that's exactly what they gave us, just 2 points. But now if you want to determine the equation of a line in a plane, we need more than that. We need a slope as well. So this one is a good one to break down into stages and steps. If all you're given is 2 points like this, that automatically implies a good step one is compute the slope. So we have to dig back into section 3.2, get the formula for the slope. We'll write that down momentarily and compute it out. Preparation for the formula for the slope would be to write in that this is x1, y1. This is x2, y2. And next big preparation is, it's always a very good idea to write out the whole formula. Just like we mentioned on these notes, that's a great way to memorize these formulas. So go y2 minus y1, divide by x2 minus x1. Then just carefully plug in this information. I'll put in the negative first so I don't get tripped up with the double negatives. Y2 is this coordinate 4. Y1 is this coordinate -2. And then do it all over again. Negative sign in the middle. X2 is -3. X1 is a +1. And now we're home free. We just need to simplify this. In the numerator, the double negation becomes plus. So this is 4 plus 2. The denominator becomes a -4. So this is -6/4. We do have to simplify our answers. This is required for full credit on quizzes, exams, and the Newton homework has a way of complaining about these things. But this one's fast. Just divide by 2 in the numerator denominator to get -3/2. And we've got it. That's our slope. So this is kind of a longer problem. It's really a good review problem as well. This was one whole problem in section 3.2. But now it's just step one in this problem where we're finding the equation of the line through those 2 points. Step two is then to use the point, slope, form of a line. That means we need to use a point. We already have the slope, so that's done. And you can use either point you like, but this point slope form of a line goes y minus y1 equals the slope m times x minus x1. So it's usually pretty natural to consider this to be your x1, y1, the one we labeled as x1, y1 already. Remarkable thing about these facts is you could just use this one as your x1, y1, -3, 4, and you'll get the same exact line when you solve for y. So we'll make a substitution here, here, and here, following the color coding on the notes so far. This will be y minus, double negation just creeped in on this one, y minus a -2, equals the slope m. We computed that as -3/2 in the steps above, times x minus x1 is a +1. And that's our 3 substitutions. There's more. Here's step 3. Solve for y. That's a step 3 because the instructions asked for the slope-intercept form. So last steps, get the variable y completely isolated, and we're done with this one. There's a good amount of algebra already to this stage. Any questions at all, folks, with any of these particular steps? Okay, let's crank this out then. On the left, this just converts to y plus 2. On the right, we're distributing a fraction into that group. First, it's -3/2 times x. Here to here, it's -3/2 times -1, so not too bad. That's just now a +3/2. And because we're dealing with 3/2, let's go to this +2 here and put it under a denominator of 2. That 2 will then convert into 4/2, the same as the 2 we had before, but now when we go to subtract 4/2 from both sides, the fraction arithmetic is just a little bit easier to handle. So cancellation on the left just gives us y, then minus 3/2 x. Here in this column, it's 3/2 minus 4/2. They have the common denominator, so you're just subtracting 3 minus 4 in the numerator. That gives us minus 1/2. And finally, that's the answer. This is the one and only one equation. There's no other way to write this when y is solved for that goes through those two lines, or excuse me, goes through those 2 points. Well, this one's a tougher one for sure. I have a couple more tricky ones to take a look into. Any questions whatsoever, folks? Finishing off this one. Okay, in the interest of time, let's see how long these ones might be. This one's not too bad. This one looks like it's going to be a nasty one. We might have to save part E for when we come back on Tuesday's class, but that's just as well. This is not a good one to run through. I think we actually have a good amount of time to finish off part D. So we'll make this one our official one right before going on onto the weekend for this class. It says it passes through a point, 1, 4. So I'll call that an x1 and a y1. And it's going to be parallel to this line right here. We want the equation of a line that goes through that point and at the same time is parallel to this line. That seems like a lot to ask for, but really, don't forget parallel just means we want the same slope as what this line is. What this line has as a slope is a better way to say. How do we get the slope of that line? We just go back to slope-intercept form. That's what we were doing at the end of the last section notes. Solve for y. That means we need to add x to both sides. 2y equals x plus 8. Then divide all sides by 2. Y is going to be 1/2 x plus 4. So the slope we have here is 1/2. And that means the slope that we want is going to be 1/2 as well. I think what makes this problem kind of confusing is not the amount of algebra you have to do. It's not as bad as the last problem. That was a good amount of algebra. What's confusing about this problem is you're building the equation for a line, and there's already an equation of another line here, so it's kind of a distraction. So one way to kind of organize your thoughts on this is you could write down our line has, and just remind your brain that we're building this totally new line. Once we get what we want from this one, we're done with it. We're not even going to look at it again. So our line has point 1, 4. That's the x1, y1. And slope m. Because it said it was parallel, the slope has to be exactly 1/2. If it said perpendicular, we would have had to flip it. It would now be a 2 and take the opposite sign. So perpendicular would have put a -2 here, but parallel puts in exactly 1/2. So the color coding here in yellow is connecting the dots with parallel. Our line just has to satisfy these conditions. Now, once we have that, we put down the point slope form of the line. Let's put a little border here so the line above is no longer a distraction. Go y minus y1 equals the slope m times x minus x1. Now, same steps as before. Once you get to this stage, you're basically home free at this point. All you're doing is plugging in information that you see on paper. Y1 on the left is 4 from the given point 1, 4. The slope m from the left is 1/2. Then it will go x minus x1 is 1 from the point given on the left as well. The whole problem is done once we solve for y, so we're just about there on this one. We'll have y minus 4 equals, distribute this here to get 1/2 x, distribute here to here to get minus 1/2. Same conundrum as before, that -4 and the -1/2 are just kind of incompatible. One's a fraction, the other is not. So put a 2 here, make this an 8. 2 goes into 8 4 times, so we didn't change -4. We just made it compatible with this one over here. Now we can add 8/2 to both sides in this way. And the slope-intercept equation of the line is y equals 1/2 x. Then over here, it's 8/2 minus 1/2, so plus 7/2. So we did it, folks. That's the one and only equation going through 1, 4, also parallel to this line here. You don't have to plot both lines to check if they're parallel. Sometimes that work is harder than doing the actual problem because you have to plot these lines perfectly like a machine. But we can get the perfect right equation algebraically without being a robot. Just follow these kinds of algebraic steps. Any last questions at all, folks, on this problem here? Okay, I mentioned that the next problem is harder, so we'll come back to these notes when we come back to Tuesday's class. We'll take a look at this one. I think there's one kind of similar to this one in the homework as well, so it kind of says we really should look at that one. Then after that, we'll be moving into the chapter 4 material. Really, it's just handling 2 lines at once as opposed to just the one. But have a great night, folks. Have a great weekend. If you have any questions while you're working the homework or the new quiz number 2, don't hesitate to reach out by email. I'll be happy to help out. Take care.